Hi, welcome back to Chapter 17, second lecture for the semester. In this lecture, we're going to start off talking about these target cells. So the target cells are what the hormones are going to move to. They have to have receptors for the hormones to bind. And the number of receptors is going to vary depending on the amount of hormone in our system and the amount of hormone needed by the body. Most target cells have more than one type of receptor. And so they might have receptors for 2 or more hormones. So different target cells are going to be able to bind different hormones. The number of receptors for the hormone will determine how much hormone can bind to any given cell. I always use oxytocin as my example for this, and pregnancy. So at the beginning of pregnancy, oxytocin starts being released in small amounts. So oxytocin has more than one function. But one of the functions, which we talked about last semester when we talked about positive feedback, was in uterine contractions during labor. And so oxytocin binds to receptors on the surface of the cell and on the surface of the cells of the uterus. When you're not pregnant, not as much oxytocin is released at any given time, and because of that, and we don't have as many receptor cells for the oxytocin. So it kind of monitors the amount. We don't need too much oxytocin, so we downregulate the number of receptors. But when we get pregnant, then we have a small amount of oxytocin in our system. We need more oxytocin because that's what's going to stimulate or elicit those contractions during labor. So we start upregulating the number of cell receptors for oxytocin on our uterus. This allows for more oxytocin to bind. Once we have given birth, again, we have, at this point, we're going to have a lot of oxytocin in our system, but now we don't need as much. And so we're going to start downregulating, so reducing the number of receptors on the surface of our uterus. So I told you that target cells have more than one, in general, have more than one receptor cell. So we have, we might have receptors for growth hormone and thyroid hormone, or oxytocin and I don't know. I can't think of one with oxytocin, so I'm going to take that one back. And instead, I'm going to use estrogen and progesterone, okay? And these hormones can have different effects, okay? So sometimes when you have more than one hormone binding at the same time or binding, they can have synergistic effects. So synergistic effects, just like with the muscles, that means they work together. So an example here, we have follicle stimulating and testosterone. Both work to produce sperm in males. Permissive effects occur when one hormone paves the way for the other hormone. So the best example here is estrogen and progesterone. Estrogen first goes into the uterus and prepares the uterus for the actions of progesterone. And then antagonistic effects are opposite effects. So one does one action, the other does the complete opposite action. So in this case, your target cell, if it binds insulin, it's going to lower our blood glucose because those cells are going to take glucose in, building up glycogen. If glucagon binds, then you're going to break down the glycogen and release glucose, so raise that blood glucose level. So hormones are controlled. There are 3 major mechanisms for controlling hormone, but they all use a negative feedback loop. So An example of a negative feedback loop and the most common mechanism of hormone control is through hormonal control of hormones. And hormonal control of hormones means a hormone stimulates the production of another hormone, okay? So this is showing hormonal control of hormones. We have corticotropic releasing hormone, which is a hormone, a releasing hormone from the hypothalamus. And that's going to stimulate our anterior pituitary gland to release adrenal corticotropic hormone. This stimulates the adrenal cortex to release cortisol, which is a glucocorticoid. Cortisol is going to then enter the blood. And so when we have an increase in cortisol, that's going to tell our anterior or our hypothalamus, hey, we no longer need corticotropic releasing hormone to stimulate the anterior pituitary. So hypothalamus is going to stop releasing corticotropic releasing hormone. This stimulates the anterior pituitary, or this stops stimulating the anterior pituitary. So it stops producing the adrenocorticotropic hormone. Adrenocorticotropic hormone no longer is being released, and so our adrenal gland is no longer being stimulated to release glucocorticoids. And so that is a negative feedback loop. And if you notice, the hypothalamus is the major player that started this whole cascade. So the hypothalamus is actually the master of the endocrine system. The anterior pituitary, or not anterior pituitary, the pituitary gland itself is the master endocrine gland. So there is a relationship between the hypothalamus and the pituitary gland. The hypothalamus is a region of the brain found within that diencephalon, and it controls the pituitary gland. And in controlling the pituitary gland, it is the master of the endocrine system then, because the pituitary gland is the master endocrine gland. So the hypothalamus sends signals to the pituitary gland, and you can see here the hypothalamus, you can see the pituitary gland here, and then it hangs on a stalk, so they're attached by this infundibulum. The hypothalamus then stimulates the pituitary gland to secrete hormones, depending on if it's anterior or posterior. Okay. And so here again, you can see that hypothalamus, which is controlling the pituitary gland. The pituitary gland has two regions. It has an anterior and a posterior region. The anterior region of the pituitary gland is endocrine tissue, so it produces and secretes its own hormones. The posterior pituitary is not endocrine tissue. It's actually nervous tissue, so it's more neurosecretory. And so you can see these nervous, or these axons running to the posterior pituitary that will stimulate the posterior pituitary to release hormones. The posterior pituitary does hold hormones. It doesn't produce them. It holds hormones produced by the hypothalamus. The two hormones that the hypothalamus produces and stores in the posterior pituitary are oxytocin, an antidiuretic hormone. And so this is typically thought of as the neural hypophysis, because the hypophysis is the pituitary, but the neuro means that it is nervous system tissue. So oxytocin is produced by the hypothalamus, stored in the posterior pituitary, and released when the hypothalamus tells us to, or tells the posterior pituitary to release hormones. The targets are mammary glands and the uterus, and it stimulates uterine contractions and milk production. Both are forms of positive feedback. or both are controlled by positive feedback mechanisms, I should say. Antidiuretic hormone is produced by the hypothalamus, stored in the posterior pituitary, and released when the hypothalamus tells it to. The target is the kidney, and it increases the number of aquaporins. And this causes us to increase the amount of water that we keep in our body so we don't release too much water and become dehydrated. So here you can see the picture, a person having to go to the bathroom. Maybe they don't have enough antidiuretic hormone, or maybe they just have too much, they've waited too long, who knows, right? So a disorder associated with antidiuretic hormone is diabetes insipidus. So when you hear the term diabetes, almost everybody assumes it's associated with the amount of glucose in our blood. But diabetes insipidus is not. Diabetes just means that we are producing a lot of urine. So we're releasing a lot of fluids from our body. Diabetes insipidus is a disorder where our body either isn't responding to antidiuretic hormone or our body isn't producing antidiuretic hormone. And in this case, we can produce tens of liters of urine daily. So a typical individual will release about 1 to 2 liters of urine, depending on how hydrated we are. In diabetes insipidus, the individual can produce 20 or more liters of urine in a day. So it's a lot of urine. And so this is where I always like to remind people, we only have a certain amount of blood in our body. So our blood plasma, which is predominantly water, is about, or we only have about 5 to 6 liters of blood, which I think we've talked about in the past. If not, I'm mentioning it now. And so if we have 5 to 6 liters of blood and we're getting rid of 20 liters of fluid, that means we have more fluid being released than we have in our body. That can keep us moving. So people have to drink a lot more fluids as well when they have this disorder. All right, I'm going to stop here because this is a great place to stop. It's been 12 minutes and we don't want it to be too long. Have a great day. Bye.